Restriking voltage is the transient voltage that appears across the separating contacts of a circuit breaker immediately after current interruption, particularly at the first current zero when the arc is extinguished. So I have explained this concept already in my previous lecture when I was discussing about the TRV, the transient recovery voltage, and there I have discussed the three type of the voltage in case of TRV. So the restriking voltage is the, here we can see that you can see out here the transients. These transients are basically the restriking voltage. So this part from here to here, we usually call it ARV. We usually call this part as ARV. Then from here to here, we say it restriking voltage. And from here to here, we call it recovery voltage. So this part of TRV is usually known as restriking voltage. So what does it represent? It represents the initial voltage stress trying to re-establish the arc across the breaker gap before the insulating medium has regained sufficient dielectric strength. So it is responsible for again starting the arc in the circuit breaker. So it typically has high frequency and oscillatory nature. It has oscillatory nature, often dominated by the system's natural RLC resonance. And the frequency ranges are the frequency range in the range from 1 kilohertz to from 1 kilohertz to 10 kilohertz. So it has a high frequency. These striking voltage transients have high frequency from 1 kilohertz to 10 kilohertz. So if the voltage rise faster than the dielectric recovery, it may cause the arc to ignite, a phenomena known as restriking. So now we will perform the derivation of restriking voltage. Here I have derived the equation for restriking voltage. We will use the same circuit diagram in which we have an inductor L and capacitor C connected in parallel with each other. Here is a circuit breaker and here the fault is applied. So if we will apply KVL to this circuit diagram, then this Vm is equal to L di by dt plus 1 by C I of t dt, where you know that I of t is equal to current after extinction of arc and 1 by C I of t dt is equal to voltage across capacitor. So 1 by C I of t dt is basically the voltage across capacitor and this term is the voltage across the inductor. Now we will take the Laplace transform of both these terms. So Laplace transform of di by dt, because L is the constant, it will, you know well that Laplace transform di of dt is equal to S I of S and Laplace transform of integral of I of t is equal to Is over S. So then the Laplace transform of KVL gives, so with L we will replace SIC and with 1 over C we will replace with IS over C. We'll solve this equation for I of S. We will take first common IS from this equation and the I of S will be here in the form of common and LS plus 1 over C will remain inside the brackets. So now we will solve this equation for I of S. So I of S is equal to Vm by S, and from here it is in numerator and the other side of the equation it will now be in the denominator. So now we will multiply this S inside these brackets. So this term will become Is is equal to Vm divided by Ls square plus 1 over C, and we have marked this equation as equation number 1. Capacitor voltage in Laplace, we know that if a capacitor is connected in a circuit as V is equal to IR, similarly for capacitor in Laplace domain, VCS is equal to 1 over CS times IS. 1 over CS is basically its impedance and IS is the current. So current times impedance is equal to voltage. So here is our equation number 2. So now what we do is that we will use this equation number 1, I mean the value of current from equation number 1, and substitute this I of S in equation 2. So we will put this value of IS from here, and the equation number 2 will become now VCS is equal to 1 over CS will remain like this, and IS will be replaced with VM over LS square plus 1 over C. Now we will multiply, or we will make this as a one fraction Vm over Cs Ls square plus 1 over C. Now we will multiply C inside these matrices. Vm over S LCS square plus 1. Again, what we do is that we have again written this thing over here, and now this is correspond to Vm over S and 1 over L S square LC plus 1. Now what we do is that we have now took LC common from here, LC common from here, and inside the brackets we are left with S square plus 1 over LC. And we know that omega n, we know that from here, this omega n is equal to 1 over, omega n is equal to 1 over under root LC. So omega n square is equal to 1 over LC. So we can replace this 1 over LC with omega n square. Therefore, this equation 3 can now be written as VCS is equal to Vm over, here we have LC, we have replaced LC with 1 over omega n square, and in the whole form we have written as 1 over omega n, and the whole bracket is for square. And inside the brackets we have S times S square, 1 over LC is replaced with omega n square. So now this omega n, this omega n will can be go in the numerator side. So when it will move upwards towards the numerator will now become omega n Vm, omega n Vm, and inside the brackets we have placed omega n S times S square plus omega n. Why we have done this? We have done this because we want to basically have a standard form of the equation, just like this omega n over S, S square plus omega n square. And why we need this equation in terms of this form? The reason is that if we want to now take the inverse Laplace transform this equation, it will give us omega n over S square plus omega n square. This will give us sine omega n t. Now what we do is that we will take the integral of this from 0 to t. 0 to t we have taken that, and we have applied the integration. After having the integration, we have cos omega n t from 0 to t. We replace the value of t and 0 while applying the limits on cos omega and t. The equation is simplified, and we have left with Vm times 1 minus cos omega and t, and this omega n will cancel out this omega n. So now we have VCT is equal to Vm 1 minus omega and t. So now we can see that we can have the maximum value of VC when we have when we can have the maximum value of VC, we can have only the maximum value of VC when cos omega n t is equal to minus 1. Because when cos omega n t is equal to minus 1, 1 minus minus 1 will become equal to 2. So 2 times Vm. So how we can get cos omega n t is equal to minus 1? So we can have the value of cos omega n t is equal to minus 1 only when omega n t is equal to pi. When omega n t is equal to pi, then we have cos pi. I mean, instead of omega n t, we will replace with pi. So cos pi will equal to minus 1. So it means that we need omega n t is equal to minus 1. So here omega n t is equal to pi. So what will be the value of t we can have? Then the t is equal to pi over omega n. And if we replace omega n was 1 over under root LC, so the t is equal to, then the t is equal to pi under root LC. Omega n is equal to 2 pi fn. So therefore fn is equal to omega n 2 pi and 1 over 2 pi under root LC. So these are the values which are very important. T is equal to pi under root LC. Omega fn is equal to 1 over 2 pi under root LC. Then we have T is equal to, then we have T is equal to pi over omega n. T is equal to pi over omega n. So we have these values which are very important. So this T is equal to pi over under root LC represent that we can have the maximum value of Vm, I mean the maximum value of the striking voltage after which time? After T is equal to P times under root LC. So the maximum value of T is T, the time for restriking voltage dependent on the circuit parameters which are L and C. Similarly, the frequency of restriking voltage, the transients in the restriking voltage, they also depend on the circuit elements that are capacitor and inductor. So the frequency and time both are dependent. So the frequency and time both are dependent on circuit elements that are L and C. So if we have the higher value of L and C, we have we will need more time. We require more time to have the more restriking to have the value of the restriking voltage. And if we have a higher value of LC, then the frequency of restriking voltage will be less. So these parameters basically tell us this thing. So now, what are the characteristics of restriking voltage? First of all, we have amplitude factor. The amplitude factor is equal to peak of transient recovery voltage divided by normal system peak voltage. So, how can we understand this thing with the help of with the help of figure? So, just look at here. This is the peak of the TRV or the active recovery voltage, which they are basically peak of transient recovery voltage TRV. So, this is the peak of TRV. Peak of TRV. So we will take this value divided by this is the system voltage. This value represented by here at this point with the dashed line. This is the supply voltage. So the ratio of both of these voltages will be equal to amplitude factor. So it tells how much. So what does it tell us? It tells us how much higher the transient peak voltage is compared to the system's regular voltage. So understandable. So typical values of amplitude factors are around 1.4 to 2 times. This transient recovery voltage can be 1.4 times to 2 times to the normal system voltage. However, the transient recovery voltage cannot be more than 2 because the peak of transient recovery voltage is 2 Vm as we have discussed in our uh, derivation that when we have the maximum voltage of voltage striking voltage when omega nt is equal to pi or cos omega nt is equal to -1 and at that time V max is equal to 2 Vm. So the maximum value could be 2. If the amplitude factor is too high, it becomes more difficult for the breaker insulation to withstand without breakdown. So this value of uh, transient recovery voltage or the amplitude factor should be as close to unity as possible. Otherwise, if its value will be more, then it means that the transient recovery voltage is high. So there is a high probability that the arc will reignite. So the second important characteristic of striking voltage is a very high initial rate of rise of voltage. So after current zero, the striking voltage across the breaker contacts rises extremely fast. That yes, we know that. This initial steepness is measured as rate of rise of striking voltage, and its units are in kilovolt per microsecond. A high rate of rise of striking voltage puts severe stress on circuit breaker insulation. So now from this figure, I can explain to you that what is rate of rise of restriking voltage. So you know that this is restriking voltage VC. So on the y-axis we have restriking voltage, and on the x-axis we have T. So the rate at which this restriking voltage steeps and it for and climbs up to the maximum value. This rate is basically known as R R R V. So this rate, how fast this restriking voltage reaches its peak or maximum value, this is known as triple RV or rate or rise or striking voltage. So this rate is very important because if this rate is less, so we have more time or the circuit breaker has more time to basically gain its dielectric strength. So a rate of rise of striking voltage, as the name indicates, because it is a rate, so we can get it by having a differentiation or derivation of the restriking voltage. So restriking voltage VCT, when we take the derivative of it at with respect to time, we actually get the rate of rise of restriking voltage. So the value of restriking voltage is, you know, that Vm1 minus cos omega nt. So when we take derivative, it come out to be Vm1 minus cos omega nt. So when RRV is equal to 1. So when we can have its maximum voltage, we can have its maximum voltage Vm sine omega nt. I mean this is the value of RRV 1 minus cos omega nt, and we took its derivative. When we took its derivative, it becomes Vm sine omega nt. So we can have the maximum rate of rise of voltage when we have the value Vm, and we can have this when omega nt, I mean the maximum value could be Vm omega n, and this could be when sine omega nt is equal to 1. So when sine omega nt is equal to 1, when omega nt is equal to pi by 2. So omega nt is equal to pi by 2, then sine omega nt is equal to 1. So then we can have the maximum value of RRV, which is Vm omega n. So if omega nt is equal to pi by 2 for the maximum value, then T is equal to P over 2 omega n. And if we put the value of omega n here, so T is equal to under root LC times pi divided by 2. So this value of T is also important for having the calculations in the numericals when we'll do it for the RRV. So basically there are two types of restriking voltages and they are based on the frequency. One is the single frequency oscillatory restriking voltage, and the other one is double frequency oscillatory restriking voltage. The single frequency restriking voltage means that we have only the restriking voltage occur with the change of one frequency. I mean here we have a restriking voltage with one type of frequency. You can look it here. So if we have one one type of frequency, or the restriking voltage with the one value of the frequency, then we will say it the single frequency restriking voltage. However, if we have two different types of frequencies in restriking voltage, for example, here is the one transient with one value of the frequency, and here are the other transients with the other value of the frequency. So these are the two transients with different frequencies. So then we can say that we have a double frequency oscillatory restriking voltages. So these frequencies are occur because why occur because of uh, the elements placed in the circuit. If we have a single source, for example, single resonant frequency for with using the single L and C circuit, then we have the single type of frequency, and therefore we can say that we have one clear frequency, and that clear frequency is basically the single frequency oscillatory striking voltage. And similarly, if we have here in this case for double frequency oscillatory striking voltage, we have here one circuit L1 C1, and here we have another circuit L2 C2. So therefore we have different types of capacitor and two different type of inductors. So because of that, we have two different type of frequencies. So this is known as double frequency oscillatory restriking voltage. So in this case, we have two resonant frequencies are excited after interruption. A combination of two oscillations with different frequencies. This leads to complex beating waveform. So I hope this is clear to you that what is the difference between the single frequency oscillatory striking voltage and double frequency oscillatory striking voltage. So they have their own use. However, the double frequency oscillatory striking voltage is much complex and difficult to understand as compared to single frequency oscillatory striking voltage. So now we will discuss two numericals on restriking voltage. The first numerical is a single phase equivalent circuit for studying the recovery voltage when a circuit breakers clear a fault as given below. So here we have a single phase equivalent circuit for studying the active recovery voltage where we have Vt, L and C. Here we have a circuit breaker and here we have a fault. So the value of Vt is given as Vmax, and Vmax, which is 1100 times cos omega n t. Here 314 is the value of omega n t. So what we have to calculate is we have to calculate the average value of the rate of rise of recovery voltage. I mean, we have to calculate the average RRV. The value of inductance and capacitors are already given. The value of inductance is 1 millihenry and the value of capacitance is 400 picofarad. So we know that from the problem that Vmax is equal to 11,000 volts, and the maximum restriking voltage, we also know that from our derivation that it can be 2 times of Vm. So 2 times of Vm is equal to 22,000. And the formula for average rate of rise of recovery voltage is V peak divided by T peak. So V peak is equal to T 2 Vm, and T peak is equal to, or T is equal to, we can have the value T by 1 over 2 Fn. So using the formula T is equal to 1 over 2 Fn, we can have the value of T. And T is ultimately, after putting this value here, the T is equal to pi under root LC. We have the value of L and C. Pi is equal to, you know well what is the value of pi. So T is equal to pi times under root LC. We can have the value. So after putting the values here in this equation, the average rate of rise of restriking voltage is equal to 11072 volt per microsecond, which is equal to 11.072 kilovolt per microsecond. So I hope this numerical is clear to you. If you have any problem, you can ask the question in the comment section of this video. Now we will start with the second numerical. In a short circuit test on a 3-pole 110 kilovolt circuit breaker, power factor of fault was 0.4. The recovery voltage was 0.9 times full line value. The breaking current was symmetrical. The frequency of oscillation of the restriking voltage was 15 kilohertz. Estimate estimate the average RRV when the neutral is grounded and the fault involves earth. The neutral is grounded, but the fault does not involve the ground. So now we have to calculate average RRV, but for two cases. First, when the neutral is grounded uh, and the fault involves earth, and second time, but neutral is grounded, but the fault does not involve the ground. So first of all, we know that we have a three-pole breaker. So the three-phase voltage we have 110 kilovolt. and cos the power factor is equal to 0.4, cos phi is equal to 0.4. So, and recovery voltage is equal to 0.9 times. Here it is given as 0.9 times of the full line voltage. And Fn is equal to 15 kilowatt, again given in the problem. So Vmax is equal to what? First, we will convert this three-phase voltage into phase to neutral voltage by dividing it by under root 3 and then multiply it with under root 2 to make it Vmax. So now we have phase to neutral Vmax value. We have power factor is equal to 0.4. This power factor will give us the angle theta, which is equal to cos inverse 0.4, which is 66.48 degree. Now we know that sine phi is equal to sine of angle. And why we are interested in finding out the value of sine phi? We are interested in finding out the value of sine phi because we know that VR is equal to K1, K2, K3 times Vmax sine phi. And again, why we are interested in finding out the value of VR? The reason is because the average rate of rise of restriking voltage is basically equal to 2 times of VR divided by T. So after having the value of VR, we can only calculate the value of average triple RV. And therefore, first we have to calculate the VR. Therefore, to calculate the value of VR, we need sine phi. And to calculate the value of sine phi, we need the angle theta. And from power factor, we actually done this and calculate the theta. So now we know that K1 is equal to 0.9 on account of decrease in voltage. And due to various factors, this voltage decreases, but it accounts for K1. K2 is for phase factor. Yeah, I mean that if your fault is grounded or not grounded, for example, here, if the fault is grounded, then we will use the K2 value is equal to 1, otherwise it will be equal to 1.5. Then we have K3. K3 is equal to 1 if we have phase to neutral fault, and K3 is equal to under root 3 if we have line fault. So based on all these facts, we will use these values of K1, K2, K3. Here we know that K1 is equal to 0.9, K2 is equal to 1 because we have the grounded fault, and K3 is equal to 1 because we have the phase to neutral voltages. So VR is equal to 0.9 times 1, which is equal to, we will then place the value here and we will take the value of VR is equal to 74.072 kilovolt. Now, from here, time we now we will calculate time to reach the peak value. Why we need the time to reach to calculate? Because only time and VR will be used to calculate the average RRV. So to calculate the time to reach the maximum value, we have the formula 1 over 2 Fn, and which is equal to pi under root LC. So putting this value of LC and pi in this formula, we have the value of T is equal to 33.33 microseconds. So average RRV is equal to 2 VR by T is equal to, by putting the value of VR and T here, we will get the value of average RRV is equal to 4.44 kilovolt per microsecond. Now again, for B part of this problem where the fault does not involve the ground, now we will use different value of K2 because here the fault does not involve ground. So now we will use the value of K2 as 1.5. So in this case, when we put the value of VR and VT, because the value of VR changes as it is dependent on K2 as well. So it will change the value of VR. And now in this case, the value of VR is more than the previous case. Ultimately, when we will calculate the average rate of rise of restriking voltage, its value will also be more than the previous case. So this means that the average rate of rise of restriking voltage is more in case of ungrounded faults, and it is less in case of grounded fault. So this must be very clear that in case of ungrounded fault, the average rate of rise of the striking voltage is more. So students, I hope in this lecture you have got a good idea about the restriking voltage, its different characteristics, and average rate of restriking voltage, and how we solve its different problems. If you have any problem regarding this lecture, you can ask the question in the comment section.